Hello everybody, welcome back to my Gregorius Maths video. Today, uh, today, yeah, it's completely sort of unplanned video, but I did a quick search on YouTube and I didn't see, so I was doing just, I was at my math society at school, doing a little talk on Fourier series and specifically just expanding stuff as sums of cosines. And sort of it occurred to me at the very end that there was sort of a really simple way using Fourier series to prove um, to what's it called? Yeah, to solve the Basel problem. And I did a quick dive, a little look on YouTube, just to make sure there wasn't like some video out there with like 1 million views that already did the exact same thing. And I couldn't actually see it, so I thought I might as well post this onto YouTube. I guess, yeah. So I'll just quit yapping and just get into it. So the function that we're going to be looking at to start with is the repeating ramp function. So at 0, 0, then it goes up to pi, then it goes down to 0 again, up to pi, down to 0, up to pi, down to 0, so on, so on. And on this side, up to pi, down to 0, up to pi, so on, so on. So, okay, we've got 0 here, 2 pi here, 4 pi here. And the idea is, when it's going up, we've got, y equals x, and when it's going down, it's like y equals minus x type thing. So, and it just repeats forever. So, okay, the period of this function, we can say is minus pi to pi. And so good. Okay, we can do a little Fourier series expansion of this function. And so for the coefficients, so for a, k, and again, note that this function is even, and so it will just be a sum. So we're going to write f of x equals sum from n equals 1 to infinity of an times by cosine of nx. Right, now, okay, we want to find these coefficients an. And the way to do that is the formula for that, sorry, this is plus a0. The formula for an, when n is not equal to 0, is we just do 1 over pi times by the integral from minus pi to pi of f of x times by cosine nx dx. And I'm sure there's 1 million videos on YouTube explaining why this is true. For this video, I'm sort of assuming that you're either comfortable with Fourier series or you're willing to just accept that this is the formula for an. Now, okay, in our case, this sort of splits itself up into two different bits. So from minus pi to 0, our function is y equals minus x. And from 0 to pi, our function is y equals x. So in this case, an is equal to 1 over pi times by the integral from 0 to pi of x cosine nx dx minus the integral from minus pi to 0 of x cosine nx dx. And okay, now we can integrate this. So if we use integration by parts, we do a little di, shout out to black pen, red pen. We differentiate x to get rid of the x, so that goes to 1. And we integrate cosine of nx, so cosine nx goes to sine of nx over n. And I'm realizing now that all of my pens are basically dying, so I'm just going to stick to black for now. Okay, so we times these two diagonal things together. Also, I'm just going to focus on this for now. Okay, we times these two diagonal things together, and we get x sine of nx over n, evaluated at 0 and pi. I'm just focusing on this one here. And then minus the integral from 0 to pi of sine of nx over n dx. Okay. Now, because sine of an integer multiple of pi is always 0, whenever this expression here is always going to be 0, so we don't care about it. And, well, the integral of sine of n times x is just minus cosine of n times x over n. So if we integrate this, remembering the minus sign, we're going to get positive cosine of nx over, well, we've already got one n on the bottom, so we're going to have n times n squared, evaluated at 0 and pi. Now, when n is even, cosine of n times x is going to be 1, but cosine of 0 is also 1, so when you plug in the bounds, you're going to get 1 over n squared minus 1 over n squared, which is just 0. And then, so when n is even, our coefficient an is 0. When n is odd, cosine of n times x is minus 1, so we're going to get minus 1 over n squared minus cosine of 0 is 1 over n squared, which is just minus 2 over n squared. And then don't forget that that was just the integral from 0 to pi. This integral here, in fact, what would have been better is noting that because f of x is even and cosine of x is also even, we could just say that the integral from minus pi to pi is the same as 2 times the integral from 0 to pi. Yeah, that would have been better. 2. So if we times this by 2, we get minus 4 over n squared. And then also, don't forget that we have to divide by pi, so minus 4 over pi n squared. And this is when n is even. Sorry, odd. Okay, good. Now, the last step is to find a0. And to find a0, we have to do, I believe it's 1 over 2 pi times by the integral from minus pi to pi f of x dx. Again, because f of x is even, this is just 2 times the integral from 0 to pi. So 1 over pi times the integral from 0 to pi of fx, which is just the integral of x, because from 0 to pi our function is just y equals x. Integral of x, x squared over 2. So we get 1 over pi times by pi squared over 2, which is just pi over 2. Good. So let's collect all this information together. We're writing our repeating ramp function as this sum here of cosines plus a constant. The coefficients of our sum, an, are given by their 0 when n is even, and minus 4 over pi n squared when n is odd, and a0 is equal to pi over 2. So, to write this all down nicely, we have that, if I'm just going to do this in the corner, we have that f of x is equal to pi over 2 minus, so a1 is just 4 over pi cosine x, a2 is 0, a3 is 4 over 9 pi, so minus 4 over 9 pi cosine of 3x, minus 4 over 25 pi cosine 5x, and so on. This is equal to, if we just factor out the 4 over pi over 2 minus 4 over pi times by cosine x minus cosine of 3x over 9 minus cosine 5x over 25 minus da da da. Now, good. Okay, so we've found our series expansion for the repeating ramp function. And here's where I thought, so that was originally where I planned to end the talk at Maths Society and sort of say, oh, I plot it on Desmos, look, it gets close to the repeating ramp function, talk done. Then I realized, wait, something kind of cool is happening here. Sorry, this should be pluses, by the way, because I factored out a minus sign. Then I realized, wait, something cool happens. What if I literally just plug in x equals 0 on both sides? Well, then I get, because f of 0 is just 0, so I get 0 equals pi over 2 minus 4 over pi times by 1 plus 1 over 3 squared plus 1 over 5 squared plus 1 over 7 squared plus and so on and so on. Then, if I rearrange this, I just get 1 plus 1 over 3 squared plus 1 over 5 squared plus 1 over 7 squared and so on is equal to, well, if I add this whole thing on both sides and then times by pi over 4 on both sides, we get pi squared over 8. Hold on, okay, first of all, nice result, cool. But then, if you just say we're trying to find the sum from n equals 1 to infinity of 1 over n squared, and we've found all of these, the missing ones are 1 over 2 squared, 1 over 4 squared, 1 over 6 squared, 1 over 7 squared. So this is just equal to the sum from n equals 1 to infinity of 1 over 2n minus 1 all squared, so these are the odd ones, like here, plus the sum from n equals 1 to infinity of 1 over 2n all squared. Good. Now, this is equal to, we've just used Fourier series to say pi squared over 8. And this is equal to 1/4 times our original sum from n equals 1 to 0 of 1 over n squared. Because if you expand this out, you just get 4n squared, take out the quarter. Nice. So that means that 3/4 times this, if you just subtract this from both sides, 3/4 sum from n equals 1 to infinity 1 over n squared equals pi squared over 8 times by 4 over 3 on both sides, and you get the sum from n equals 1 to infinity of 1 over n squared equals pi squared over 6. I'm just going to write that in a pen that works. Pi squared over 6. Nice. Yeah, I mean, I think that's really quite a simple proof of the Basel problem. I'll probably put a clickbait title saying, the simplest proof. And I mean, if you take this series expansion for granted and just say, this is equal to this, which doesn't take too much difficult work, I don't think. You just have to integrate cosine and sine. And then you literally just plug in x equals 0. And I mean, I don't know, I don't think I've seen this anywhere. I'm sure, okay, I'm not gonna, I'm sure someone else has done this before. I just haven't personally seen it, so I just thought, in the spirit of keeping Gregorius Maths active, I thought I would post it to YouTube, but I think this is really quite a simple proof. I thought, okay, I might as well post it online. Yeah, and there you go. Basel problem shown via Fourier series. Yeah, that's all I had to say, so goodbye.